Good morning everyone, this is Group 15's video presentation. We will be presenting on Group 15 elements, also known as nitrogens from the periodic table. These groups include nitrogen, phosphorus, arsenic, antimony, and bismuth. These elements are extremely important in both nature and industry. They play key roles in biological systems, fertilizers, electronics, medicines, and even explosives. In this presentation, I will explain their occurrence and extraction, their important compounds, and finally their chemical behavior, especially focusing on nitrogen chemistry. Group 15 elements include nitrogen, phosphorus, arsenic, antimony, and bismuth. As we move down the group, the elements change from non-metallic to metallic in nature. Nitrogen and phosphorus are nonmetals. Arsenic and antimony are metalloids, and bismuth is a metal. This gradual change affects their reactivity, bonding, and physical properties. Nitrogen makes up about 78% of Earth's atmosphere, so it is very abundant. Industrially, nitrogen is obtained by fractional distillation of liquid air. Since nitrogen has a lower boiling point than oxygen, it separates easily. In laboratories, membrane separation techniques are also used, where oxygen passes through membranes faster than nitrogen. Liquid nitrogen is especially useful because it allows easy storage, cooling, and provides an inert atmosphere for experiments. Phosphorus does not occur freely in nature because it is very reactive. It is found mainly in phosphate rocks, such as calcium phosphate. Industrially, phosphate ores are heated with silica and carbon in an electric arc furnace. This produces phosphorus vapor, which is then condensed and stored underwater to prevent it from reacting with air. Most phosphorus produced this way is converted into phosphorus pentoxide and then hydrated to make phosphoric acid, which is widely used in fertilizers. Arsenic is usually obtained as a byproduct from copper and lead smelting. It can also be produced by heating arsenic ores without oxygen, causing arsenic to vaporize. Antimony is extracted from the ore stibnite by heating it with iron. Iron removes sulfur, leaving behind pure antimony metal. Bismuth occurs mainly as bismuthinite and bismite, often alongside copper and lead ores. It is extracted during the refining of these metals. Nitrogen is used to create inert atmospheres in fertilizers, plastic, and explosives. Phosphorus is used in matches, pyrotechnics, detergents, and fertilizers. Arsenic is used in semiconductors and solar cells, while antimony strengthens alloys and is used in electronics and flame retardants. Lastly, bismuth is used in medicines, especially for stomach treatments, and as a safer alternative to lead. Nitrogen gas is very stable due to the strong triple bond. To make nitrogen reactive, it must be activated. There are three main methods. Number 1, biological nitrogen fixation by bacteria using the enzyme nitrogenase. Number 2, the Haber process, where nitrogen reacts with hydrogen under high temperature and pressure to form ammonia. And number 3, synthetic activation, where nitrogen binds to metal complexes, helping scientists understand and improve nitrogen chemistry. Nitrides are compounds where nitrogen has a negative 3 oxidation state. They can be ionic, covalent, or interstitial. Many nitrides are extremely hard, thermally stable, and used in industrial tools. Azides contain the N3- ion. They are toxic, unstable, and often explosives. Metal azides, such as lead azides, are used in detonators. Group 15 hydrides have the general formula EH3. Examples include NH3, BH3, ASH3, SBH3, and BIH3. As we move down the group, thermal stability decreases, while toxicity increases and boiling point increases. Ammonia is special because it forms hydrogen bonds, making it more stable, more soluble in water, and a stronger base than the other hydrides.
Hi guys, and now we are going to the next part where I, Adindo with matrix number BC252741, will explain about halides, oxides, and oxoanions of the group 15 elements. So we will start with halides. Some of the properties of halides are the oxidation states of +3 and +5. +3 oxidation state is more stable compared to +5 due to the inert pair effect. Secondly, the lighter elements form covalent bond. This is due to high ionization energy and high electronegativity. And thirdly, heavier elements form ionic bond because it has lower electronegativity, thus it acts more metallic. And next, we will look at the halides. So first we have the nitrogen halides, which can only form an X3 since nitrogen does not have d orbitals. And the stability ranking for nitrogen halides is the biggest stability is NF3 followed by NCl3 and Ni3. This is because the bigger the size of the halogen, the weaker the NX bond, thus it is easier to break. Secondly, phosphorus halides. Phosphorus can form both px3 and px5, meaning it can have +3 and +5 oxidation states. Trihalides react with water to form phosphorus acid, and the bond strength decreases from Pf to PCl and PBr. This is because the smaller the size of the halogens, it will have a better overlap, thus it will lead to a stronger bond. Third, arsenic halides. Most arsenic halides form AsX3. AsF5 exists since F is small and it can stabilize high oxidation states. And lastly, antimony and bismuth halides. They both prefer +3 oxidation state also due to inert pair effect. And here, inert pair effect means that there is poor shielding from inner electrons towards valence s orbital electrons, which means that when the shielding is poor, it leads to a higher effective nuclear charge. And next, we will look at the oxides of nitrogen. So, the first one we have nitric oxide. The oxidation state is +2. It can instantly oxidize to NO2 when exposed to air, and it acts as a neutral oxide. Second, we have dinitrogen monoxide, N2O. The oxidation state is +1, and it has characteristics of a mild oxidizing agent, and it is not really reactive. Example of preparation of dinitrogen monoxide is by heating ammonium nitrate. Thirdly, we have nitrogen dioxide, NO2. The oxidation state is +4, thus it is a strong oxidizing agent. It can also dimerizes to form N2O4. Fourth, we have dinitrogen pentoxide, N2O5, with the oxidation state of +5. Thus, it is a strong acid and it reacts with water to form 2 moles of nitric acid. And lastly, we have dinitrogen tetroxide, N2O4, with the oxidation state of +4 and it exists as a colorless gas or a pale liquid. And next, we will look at the oxoanions of nitrogen. There are two. One of them is nitrite, N2O-. The oxidation state is +3. Some of the properties of nitrite is that it is easily oxidized, it is common in food preservatives, and it reacts with oxygen to form nitrate. And the second one, nitrate, NO3-. The oxidation state is +5, and the properties include acting as a strong oxidizing agent, and it is thermally stable. And some of the key trends that we need to remember is the acidity increases with the oxidation state. So, for example, we can see here that from N2O to N2O5, the acidity increases. The explanation is, the higher the oxidation state, it will lead to more negative charge on the nitrogen, which means that the nitrogen will pull more electron towards it. Thus, the OH bond is easier to break. And lastly, we will look at the table of oxoanions of phosphorus, arsenic, antimony, and bismuth. And here we can see the oxidation states for phosphorus, arsenic, and antimony are +5 and +3. Meanwhile, for bismuth, it is mainly form +3 oxidation state. And when we talk about the stability of the elements, from phosphorus to bismuth, the stability decreases. as we can see, phosphorus is very stable, and for arsenic and antimony it is less stable compared to phosphorus, and for bismuth it is almost not stable at all. This is due to the strong metallic nature of bismuth. The ionic bonding starts to dominate, and also because of the inert pair effect. And lastly, we will look at the important trends that we need to memorize. First, the ability to form oxyanions increases from phosphorus to bismuth. Why? This is because from phosphorus to bismuth down group 15, the atomic size increases, which leads to a weaker electronegativity and a more metallic character. Second, polymerization tendency. So, for phosphorus, it has a strong tendency to polymerize, and for arsenic, it is limited, and for antimony and bismuth, almost no tendency to polymerize due to the effective pi bond overlap, which decreases down the group. And third is the acidic nature of the oxo acids of group 15 elements. This is due to the decreasing electronegativity and bond polarity down the group 15.
Now, what is actually condensed phosphate and the uses of it? Condensed phosphate, multiple orthophosphate molecules linked together, forming chain, rings, or branch structures. Orthophosphates means the simplest form of inorganic phosphorus in water. Now, what are polyphosphate used for? Sodium triphosphate as a builder for synthetic detergent, which forms stable complexes with calcium and magnesium ions in hard water. Next, for food-grade sodium triphosphate used in curing of hams and bacon, interact with protein and leads to good moisture retention during curing and improve the quality of chicken and seafood products. The last one is the phosphate is widely used as an essential fertilizer. Next, what is actually phosphazine? We're going to look at the introduction and key characteristics for phosphazine. Phosphazine contain P and phosphorus nitrogen bonds. Number 2, they can form cyclic or polymeric structures, and they're also known for being highly flexible, similar to elastomer. And next, they have wide range of structure, ring, chain, and polymer. Oxygen atoms in PO compounds can be replaced by NR or NH groups, and they also behave similarly like silicon. We have 3 types of phosphazine. For the first one, we have cyclic phosphazine. Number 2, we have substitute phosphazine, and number 3, we have polymeric phosphazine. And why they are metal? Because they are highly flexible, which is useful for rubber-like material. And they're also versatile structures, mimic silicon chemistry. And the last one is they have strong PN bonds, make them important in materials in chemistry. What is organometallic compounds of arsenic, antimony, and bismuth? Organometallic compounds of arsenic, antimony, and bismuth, for general features, contain a metal carbon MC bonds where M is arsenic, antimony, or bismuth, and its common general formula is R3M. R is alkyl or aryl group. Oxidation state of the central atom is +3, and it shows trigonal pyramidal geometry due to one lone pair on M. And stability increases down the group, which is arsenic has the lowest metallic characters and bismuth have the highest metallic character. For bonding and structure, MC bond strength decreases down the group. Lone pair become less reactive from arsenic to bismuth, which is inert pair effect, and it has heavier element. Antimony and bismuth show more metallic and ionic character. For physical properties, many are volatile liquids or low melting solids. They often have strong and unpleasant odors. Air and moisture sensitive, especially arsenic compounds. For chemical reactivity, can undergo oxidation to +5 state and more common for arsenic and antimony. It reacts with halogen to form R2MX or MX3.
Hydrolysis may occur, producing toxic byproducts. For toxicity, arsenic organometallics are extremely toxic. Antimony compounds are toxic but generally less than arsenic. Bismuth compounds are the least toxic in this group. And lastly, for the users, is arsenic compound is historical pesticide, limited semiconductor use. And antimony compound is a flame retardant, catalyst. Bismuth compounds is for pharmaceuticals and environmentally safer materials. Now we are going to look about the phosphide and arsenide. For phosphide, it is binary compounds containing phosphorus and metal. Usually show strong covalent or ionic bonding, and they are commonly used in semiconductor materials and metal alloys. Some phosphide react with water or acid to release toxic phosphine gas. For arsenides, compounds formed between arsenic and metals or metalloids often have metallic or semi-metallic properties, and they are also used in electronics, especially in semiconductor devices. They are also highly toxic and pose serious health hazard if mishandled. Then we have antimonides and bismuth. For antimonide, binary compounds consisting of antimony and a metal. It exhibits properties between metals and nonmetals, widely applied in thermoelectric materials and semiconductors. The last one is toxicity is present but generally lower than arsenide. For bismuth, it is compounds formed between bismuth and metal, typically more metallic and stable compared to other group 15 compounds. They used in alloy and some electronic application. It also considered less toxic than phosphate, arsenide, and antimonides.
Hi, so I will briefly explain about the oxohalides of group 15. Oxohalides include nitrosyl halides and nitrile halides, which are known to be highly reactive halogenating and fluorinating agents. They are usually prepared by the reactions of halogens with either an O or nitrate ions. Another important group of oxohalides is the phosphoryl halides, mainly POCl3, POBr3, and POI3. These compounds contain a strong phosphorus double bonded to oxygen, which gives them highly reactivity. POCl3 is a colorless liquid, while POBr3 is brown, and POI3 is a violet solid. All of them are tetrahedral around phosphorus atom and easily hydrolyzed when exposed to moisture and producing foods. So halides are very important in organic synthesis. They help in producing organophosphorus compound that are widely used in plasticizers, surfactants, dyes, and pharmaceuticals and additives. They can also convert alcohol and phenols to alkyl or aryl halides, which is a key step in forming many useful products.
Okay, so we will move to the next part where I will briefly explain the oxides of group 15 elements consisting of phosphorus, arsenic, antimony, and bismuth, and why their properties change down the group. First, let's look at the overall trend. As we go down group 15, the atomic size increases and electronegativity decreases. This means that the elements gradually change from non-metal to metals. Because of this, their oxides change from acidic, amphoteric, and finally to basic. So first, we will start with starting with phosphorus. It forms P4O6 and P4O10. These oxides are strongly acidic and reacts vigorously with water to produce acids. This happens because phosphorus is a nonmetal with high electronegativity, thus it forms strong PO bonds. And as a result, its oxides act as acid anhydride. And this is the example equation when it reacts with water to produce acid. Next is arsenic oxide, where it produces As2O3 and As2O5. Arsenic oxides are weakly acidic and amphoteric, meaning that they can react with both acids and bases. since arsenic is a metalloid, its electronegativity is lower than phosphorus, so the ASO bonds are weaker than PO bonds and the acidity decreases. Moving down to antimony, it forms Sb2O3 and Sb2O5. These oxides are clearly amphoteric, which means it reacts with both acids and bases. And here the element is more metallic and the SPO bonds are even weaker. As metallic character increases, the acidic nature of the oxides become less significant, which means the oxide is no longer strongly acidic. And for antimony, this is where the metallic character starts to dominate. Finally, bismuth mainly forms Bi2O3. This oxide is basic and it reacts mainly with acids. Bismuth is a metal with a very low electronegativity, so its oxide is largely ionic and it behaves like typical metal oxides. One more important concept is the inert pair effect. As we move down the group, the NS2 electrons become less available for bonding, making the +3 oxidation more stable than +5. This is why bismuth mainly forms +3 compounds and why higher oxidation states become less stable down the group. So in summary, the change in oxide behavior down group 15 is mainly due to increasing atomic size, decreasing electronegativity, as well as the inert pair effect.